Hello, welcome back to the lectures on functional programming. In this video, I'm going to talk about lambdas and conditionals. So in the last one, we introduced the very basics of Scheme, how we could use lists. We saw the DR Rocket environment. We saw the quoting things so that we could produce our basic lists. We saw how we could use cons. Actually, let's just cons the 2 onto 1, 2, 3 to add things to a list, how we could use car to get elements, the first element off of a list, how cdr gave us everything else from the list. And we finished off looking at how define allowed us to give a name to something. And so then we can use that name as the shorthand. This is basic playing with lists. I guess we also saw the syntax and how we can do addition. Now we want to look at how we can make functions, okay? Because that is our really fundamental aspect of doing functional programming, is the ability to make functions. And the keyword for making functions in Scheme is lambda. We refer to them as lambda expressions. And so you specify lambda, and we have a set of parentheses that is our argument list. So let's say that I just wanted to make the function for adding 1 to something. Well, that would be lambda of x, and that would be given by the value x plus 1. Now if I just type that in, it says you made a procedure, which I can't really do much with. I need to give it a name. And so I'll call this incr for increment. And so if I call the increment on 5, I get back 6. Okay? And so we could define whatever functions that we want using this lambda. And the basic syntax here inside of the parentheses is lambda, an argument list. I made this so it only takes one argument. I could put an x space y, x space y space z, whatever it is. I can use longer variable names, any valid names in Scheme. It turns out that Scheme lets you put lots of things inside of names, including hyphens, slash minus signs, plus signs, division, whatever you want, because it's the spaces that matter in Scheme that say you're going from one token to the next. You just can't put in parentheses or brackets. And there are some special rules for dots. And then after the argument list, whatever you put here is what the function is defined to do. And it turns out that you can actually put multiple things inside of here. Okay. However, the immediate question becomes why? What do those do? Well, it turns out that Scheme evaluates them in order, but then it gives you back the value of the last one. So all of those other things in this case are just wasted, and we'll have to learn about how we can do side effects and stuff to things that actually have effects in addition to just calculating a value before we'd ever want to do these, because as they're written right now, all of those things are just a waste. So we have functions, and we have lists, so we have data structures, and I'd like to be able to go through and do things with my lists. So obviously I can, if I call sum like that, well, not sum, sorry, if I just call plus here, I can add up the values. What if I'm given a list of things and I wanted to add them up? There are other ways to do this, but I would like for us, if we can't write the code for adding up all the elements that are in a list, we really don't have much capability. Well, we know how to get the first element off of a list, so remember we have this thing stored in list, and it turns out that if you call plus and list, that doesn't work. There is a way to do this using a method called apply, or a function that's called apply, but we're not going to look at that yet. I just want to be able to add up all of these elements. Well, I know how to get the first one. So I could say, well, I want to plus the car of LST to the next element, which would be the cadder of LST, to the next element, which would be the caditter of LST. And note, remember, if I weren't using this syntax, this would be the car of the cooter, which would introduce another layer, and this would be the car of the cooter, which would be another layer, and then this one, the caditter of LST, would actually be nested many parentheses deep, and that would be a very long expression. Okay, so I can do that there, and it works okay, I guess, for a list with 4 elements in it. But I'd like to write something that can work with arbitrary length lists. And in most programming languages, this is where you would probably turn to iteration. You would use some type of function or some type of like a loop, for loop or a while loop or whatnot to run through it. Not in Scheme. The way that we're going to do this in Scheme, and the way that we're going to produce pretty much all of the iteration that we have in Scheme, is through recursion. And functional languages in general typically prefer the use of recursion over iteration in most situations. And so then the question is, well, how can we do that? Well, rule of thumb for recursion, so a recursive function is a function that calls itself. If you write a function and it calls itself, it has to have the ability to not call itself. Define forever is a lambda that takes no arguments, and all it does is it calls forever. Now I'm almost tempted to take back out these parentheses. They're very easy to leave out. I'll come back and I'll forever. And you can see what's going there on there. That's just running and running and running. I have to go up to my menu bars and see if I can. Okay. Whoop. Apparently Dr. Brackett did not like me doing that. Run, Control T. Okay, so I just restart everything. Let's go ahead just so that we have it. Define LST as 1, 2, 3, 4. It's worth noting there is also another function called list, which takes whatever elements you pass it and builds a list from them. Note this is different from quote. So if I wanted to quote to produce the same list, I would have done that. Because what quote does is it takes whatever follows it and turns it directly into and just gives it back to you. Now, one difference between these two is if you do some nesting here, quote is perfectly happy doing that. List, that's a problem. Okay? Because remember, by default, unless you've quoted it, what Scheme does every time it sees an open parentheses is it thinks that the first argument here is going to be a function, and 2 is not a function. So if I wanted to build this using list, I would still need to either quote that there or use list to build the list of 2, 3. Okay. That's kind of a little aside there. So if I want to write a recursive function that doesn't keep going forever, I need to have a conditional. I need to have the ability to say that one thing is going to happen where it does call itself in a certain situation, and that there has to be at least some situation where it doesn't call itself so that the recursion can terminate. And in order to do that, we need to introduce a conditional statement, and the first, most basic conditional statement in pretty much every language is if. So I can say if 0 is less than 5, give us back 4, otherwise give us back 6. Okay. And of course 0 is less than 5, so it gives us back 4. What if we change this, make it a little bit more complex? If less than 0 and the car of LST then give us the catter of LST, otherwise give us the caditter of LST. Okay, which gave us 2, and now you have to ask the question, well, is that right? Well, remember, LST is 1, 2, 3, 4. The car of that is 1, 0 is less than that, so it should give us back the second element, 2, and not give us back the third element, which would be 3. Okay, so the if expression in Scheme starts with if, which is the keyword that's bound to this. It then has inside of parentheses, it has a condition, generally inside of parentheses, though if this had been bound to some name, it might just be that name. Followed by an expression for what to do if it's true, and then another one for what to do if it's false. And so we can take this and combine it with a define and a lambda to give us our first recursive function. I like the first recursive function of factorial. It also shows off some of the math capabilities of Scheme. I'll use the full name. So I want factorial to be a lambda expression that takes a single value n. And I'm going to go ahead and hit enter here. If less than n and 2, 1, else the product of n and the factorial of the predecessor of n minus 1. And close off a bunch of parentheses and hit enter. And 5 factorial is 120. And 50 factorial is a fairly large number, and 500 factorial is an extremely large number, and 5,000 factorial is a much, much, much larger number. Okay, so this does show off some of the capabilities of Scheme and the fact that Scheme has the ability to represent arbitrarily large numbers, and it also demonstrates to us our first recursive function here, where we created our factorial. What if, let's think of another recursive function that we could write. Now, this recursive function I'm going to write now is actually built into the system. You can actually ask for the length of a list, and it'll tell you. But I would like to define our own. I'll call it, actually, using Scheme style notation, you typically don't capitalize. Scheme does not use the camel case that is common in so many other languages. You typically don't capitalize, and you use hyphens to separate words. So list length is a lambda. It takes a list. I will call it LST. And there are 2 possibilities. One is if the list is empty. Now how do we check that? So Scheme has a number of different predicates in it. Predicates in Scheme, so we saw the less than, and there's a less than, a greater than, a less than or equal to, a greater than or equal to. I want to check to see if this list is null. So how would I do that? Well, there is one predicate called null, and it basically does exactly that. It takes a list and it tells you whether or not that list is null. And so if the list is null, how long is it? Well, that's 0. Otherwise, we're going to add 1 to the result of calling list length on the caditter of LST. And that function gives us back 4. Okay, so this type of structure where you're running through a list, you have something that checks if it's null, and then something that calls, has a call that in some way is recursive on the cdr of the list. This is a very, very standard approach to doing things in Scheme. We'll see lots of this. So what about SUMList? Okay. Well, once again, this looks very, very similar. We're going to have a lambda, works on the list. If I should note that all the predicates other than the things like less than and greater than all end in a question mark, the ones that are defined. And so if you write your own predicates, you should use question marks like that to follow the standard style. So what is the sum of all the elements if it's empty? Well, 0. Otherwise, we want to add the car of the list to the call of SUMList on the cdr of the list. And we can define that function, and then I can call SUMList on LST and get back 10. Okay. Now you might have been wondering at this point, what is this area up here for? Turns out that is actually an editor space. And just so that we have these things in here, since we're going ahead and defining functions that we might want to keep around, I will go ahead and put our functions up inside of here, which will make it easier for me if I decide that I want to get back to them in future videos. And so by putting it up there, if I tell Dr. Racket to do a run, actually I did save, and I should go ahead and save. Let's go back to now. Okay. When I run on this, okay, it defines all of those things and allows me to use them. Okay, so this gives you a simple rundown of some functions that we can make using recursion. We did the first one, factorial, which does not involve a list, it's just a number, and you're running through. And this is the alternative, the Scheme alternative to writing a loop to do this. And the other two actually do take a list as their argument, and they run through it, and they have this repeated call of cdr, which gets passed in so that it keeps getting shorter and shorter, as well as a conditional check to see if it's null. So that'll be it for this video. We'll build up. What I want to do in the next video is come back and demonstrate how we can, without really adding much of this, just putting together a little bit more of the same things that we've seen so far, how I can make it so that this SUMList is fundamentally more powerful than what it is right now. So that instead of so right now sum only takes the sum. I would like it so that this has the ability to run through the list and do multiple functions. So that, and this, in fact, I guess I can finish off this video by demonstrating, in fact, that if I wanted to do the product instead of the sum, and I have a prod list here, well, that also is prod list. And because it's a product, instead of doing plus, I do multiply. And my base case, because if you multiply by 0, everything winds up being 0, changes to 1. And if we do a run here, prod list on, that'll work. I didn't get an extra space in there. But these two functions here have nearly identical code. And so hopefully it should strike you as that is inefficient to have to rewrite them that way. And so we can start to see in the next video how using a functional language allows us to do that type of abstraction. So I'll see you again soon.